Right. Hello, everyone. Welcome to our first post-training webinar. It's been a few months, but I was able to see a couple of you at our City Much conference and in other spaces and places likely in our online world. So, hello, welcome. Forgive me in my messy space I'm seeing. I just moved offices again. So, it's a little busy back there. I'm realizing maybe I should have blurred, but I hope you all are well since we've seen you in Denver this summer, and that you're staying afloat in a really challenging landscape, and that you're leaning on your people and your colleagues, your friends, and your other MCHers. So thanks for being here. This will be our first of likely two post-training webinars. We always try to do at least two, maybe a third if it's identified. But this helps with the continuing education beyond the intense 1 week course. So we have Dr. Julie Petersen. She joined us in Denver and was auditing, listening in, contributing to conversation and um, career advice and things like that. So she'll be joining us and doing the webinar today on quantitative bias analysis. We'll be kind of picking all of your brains afterwards with the next most helpful post-training webinar content or topic area. We received your thoughts right after the training course when we did our post-course evaluation, but we'll also talk about some post-training webinars that we've already hosted, maybe give some resources and recording links to those, and really find what would be most helpful for you all as we've gotten a few months out from the training course and after today's content. So it'd be helpful for some feedback there. And from there, we'll have the recording sent out from today's webinar, a short evaluation. So please complete that so it can get into our report by the end of the year. And you'll just be hearing from me over the next few weeks about scheduling our next post-training webinar. So we encourage you to ask questions, come off mute. I'll be helping monitor the chat. You see that I started recording, and I will just turn it over to Dr. Petersen if there aren't any immediate questions.
All right, great. Thank you so much, Ashley. And please feel free to call me Julie. You don't need to call me Dr. Peterson. But wonderful to see you all. Good morning or good afternoon, depending on where you're calling in from. So for today's webinar, we will be talking about quantitative bias analysis with specific focus on misclassification. As Ashley said, I am an assistant professor of epidemiology at the University of Nebraska Medical Center College of Public Health, and had the privilege to audit the class back in Denver, and got to meet and interact with a number of you, and yeah, really happy to be here today. So there are a handful of times where I will specifically call out and look for volunteers to chime in or put some ideas in the chat. But I'm not the best at monitoring the chat throughout. So if you have questions and are willing to come off mute, please feel free to interrupt me. This is informal. And if you put it in the chat, then Ashley, yes, I do appreciate you monitoring that for me in case anything comes up. So just to walk through what I'm hoping you'll get out of today. So I'm going to do a brief introduction to just kind of sensitivity analyses in general, and then we'll specifically dive into quantitative bias analysis with focus on dealing with situations where you have misclassified or mismeasured data. So I'm hoping you'll have an understanding after today about what type of bias parameters you would try to collect to do these types of kind of correction analyses. I will show you the formulas, but don't worry if you're not a formula person, that's not going to be a big focus. I'll talk about different types of validation data and how we'd go about collecting that information. Certain types of QBA analyses of increasing complexity. We'll focus on more simplistic ones for today, but I will talk through examples of kind of where you can kind of build on these. There'll be a number of examples throughout. Most of them are going to be MCH examples, but I am taking this from a prior lecture I've done, so I apologize. Some of them are also in other areas like cancer. Um, and then I'll kind of close out by talking about different ways to present and interpret your findings and best practices for this type of analysis. And there'll be a number of resources made available to you if you want to learn more. So with that, I'm sure this group is pretty well aware when you're doing really any kind of surveillance efforts or some kind of associational study, there are limitations to that work, right? If you're familiar with STROBE, which is the strengthening of the reporting of observational studies in EPI, their guidelines specifically call out that you should discuss limitations of your study, taking into account potential biases or imprecisions in your data, and to discuss both the direction and magnitude of these biases. So sensitivity analysis, kind of as a really broad term, is referring to repeating your analysis with slightly different assumptions, really getting at kind of potentially some of the limitations you have of your data, or maybe some decisions that went into how you designed your study or analyzed your data that you may feel like are somewhat subjective. So these are things like changing the definition of the way you classified someone. So maybe you had information on smoking and you said if they smoke like a pack a day, then you would classify them as like a high intensity smoker. And maybe in a sensitivity analysis, you slightly change that definition to make that cutoff higher or lower than what you had originally put. You could also do things like stratify your data or restrict it down to a particular subset of your data to try to understand maybe how sample selection is coming into play, or if there's some kind of effect heterogeneity, meaning that, an association that you're looking at might be different in magnitude among subgroups of your sample. And you can kind of think of this as like a form of influence analysis where you're seeing how much an individual or set of individuals seem to be impacting your overall results and conclusions. You could change how you are dealing with missing data. Did you use a certain kind of imputation method and you could apply a different method instead? Maybe you decide to use a completely different statistical model because you're not really sure if that model is really the best fit for your data. Ultimately, you're thinking of like how robust are your results based on these different types of decisions that you're making kind of throughout the data collection and analysis process. And sometimes you'll just see the term like uncertainty analysis. And again, it's kind of getting at this same overall concept. So here's an example from a study that was looking at intrauterine device use and risk of preeclampsia in a future pregnancy. And these investigators did kind of two analyses that would somewhat fall under this sensitivity analysis area. So one is that they use stratification to assess whether there was differences in the size of the effect or the size of this association based on an individual's number of prior deliveries. And then the second analysis they did, they restricted their data set to individuals who had at least 10 years of follow-up in order to see whether or not the results were different in that subgroup that they considered to have like better ascertainment of data on prior deliveries because they had, a longer duration of information on them. So here's the results table that kind of goes through these two findings. So you can see in this top part of the table, they have the first group are individuals who didn't have any prior deliveries, and then ones with one or more prior delivery listed below that. And if you go all the way over to the right side of the screen, you can see what their adjusted odds ratios were. And so you see that they got an odds ratio of 0.64 among the group that didn't have any prior deliveries, but basically an odds ratio of 1 for those that did have at least one prior delivery. So it looked like IUD use was really only protective against preeclampsia among those that didn't have any prior deliveries, which was interesting. And so again, they also did this other analysis. If we look down towards the bottom of the table here, where they restricted to participants that had at least 10 years of follow-up, wondering if that was somehow influencing those prior results. But if you look over again on that right side of the table there, they still saw pretty similar findings where there was a much stronger protective association among individuals who had no previous deliveries compared to those that had at least one. So, as I mentioned today, we're really going to focus in specifically on kind of classification errors. So, kind of throughout this talk and probably in your own experience, you're going to see kind of some of these terms interchangeably, but they're all really referring to basically the same thing. So, misclassification, measurement error, information bias, these are all systematic errors that are arising from inaccuracies in the data that are being collected and measured on participants that you're looking at. And this will lead to some kind of misclassification of your analytic variable status. Often I feel like EPIs are classifying people into groups. Like we don't always use like continuous measures. So for the most part, I'm going to refer to this as misclassification. So some examples of how this could come up, if you were evaluating the head circumference of an infant, that can be pretty challenging, right? Like depending on exactly where you put the measurement tape and if the baby's moving around, you might get slight differences in what that measurement comes out to be. Even things that are considered, fairly accurate, like stepping on a scale, kind of depending on, how even the floor is there, the time of day for that person, if they just ate, and also just rounding errors, right? Like that comes up. So um, even if someone individually isn't doing the measurement and you're using some kind of tool, measurement errors still are coming up constantly, right? In observational work. So two key types of misclassification. One is non-differential misclassification. So this would mean that the extent of the misclassification is the same or not different, hence non-differential, based on some other factor. And if we're thinking about, an exposure and outcome association, then we could think if the exposure is the thing that's misclassified in our data, if we're assuming it's non-differential, that would mean that the extent of that misclassification would be the same for individuals with and without the outcome. So no difference in the extent of misclassification between these two groups. And then if the disease was the thing that was being misclassified in our data, like if we had like certain cases that were inadvertently being classified as controls, then that extent of misclassification would be the same for individuals who were exposed and not exposed in our data set. So again, no difference between the groups if it's non-differential. And you may have heard this heuristic that non-differential misclassification will bias your results towards the null, which would be like if you're doing an odds ratio, that would be biasing it towards a value of 1. And often we do make this kind of assumption that if it's non-differential, that's what's going to happen. However, there are lots of exceptions where bias will not necessarily be towards the null when it's non-differential. So you really can't make this assumption, and it's really best to try to investigate it in a more quantitative way if you can for your specific scenario. And this is a really great paper if you're interested in better understanding kind of where these exceptions come up. It was published in the American Journal of Epi in 2002. And I think I can probably send out like all of the papers I talk about and all the resources after today's webinar so you guys can easily get those links. So the other type of misclassification would be differential. So this is, basically the opposite of what I said, where the extent of misclassification is not the same based on that other factor. And so you're having systematic differences in the quality of the information that you're getting between your groups. So if we're talking about misclassified exposure information, it would mean that the errors are occurring to a greater or lesser degree in your diseased individuals versus those that don't have the disease of interest. And if it's a misclassification of the outcome, then the errors would be occurring, more or less in the exposed versus the non-exposed individuals. So here enters quantitative bias analysis, or QBA. And this is really a quantitative extension of these qualitative speculations that we make, right? Like you can think of if you ever read over a scientific paper, usually towards the very end of the paper, they talk about the limitations of the study, and there they might talk about kind of the quality of the measurements and what they think it might be doing. And that's where you'll see that heuristic where, they might say, we're assuming our errors are non-differential, and so we think it's biasing our results towards the null. And so that would mean that the true association is actually stronger than what they observed. But this type of analysis allows you to actually, more directly manipulate your data to see if that heuristic would actually hold true based on a set of assumptions. So you can actually model the errors that are happening in your data based on other information that you have about the extent of those errors and who they're affecting. And the purpose of this really is to estimate that potential magnitude and direction of the bias or biases that are at play, try to quantify uncertainty, and combat human tendency towards overconfidence. There's been a lot of studies done that indicate that people tend to be pretty highly confident in their results, even though they know that there are errors at play. So I'm going to walk through an example that deals with a screening test. And so I'm sure many of you are familiar with dealing with screening data. So thinking about what would make a good screening test for a particular disease or condition. Of course, if it's inexpensive, that's always good. Easy to administer, you know, minimal or no discomfort for the individual who's being tested, that it's, reliable. You would get the same result each time it was administered, and that it has high accuracy, ideally, right? Well, it can be pretty hard to have all of these things happen. And generally, if we're doing screening on a very large group of people, we'll probably lean towards it being easy to administer and inexpensive, right? At the cost of potentially, let's say, not identifying everyone who would probably screen positive. So here's an example from this PROTECT study where they were looking at the association between having a family history of prostate cancer and whether or not an individual themselves ended up having prostate cancer. And so here's just their 2x2 table and their odds ratio that they found of 1.64. However, here they knew that the screening test that they were utilizing for prostate cancer was a PSA test, and it is subject to misclassification where it isn't going to be able to capture and identify everyone who actually has prostate cancer. So I'm a pretty visual person, so I like to kind of think about it this way. So this would be like, in an ideal setting where we knew exactly everyone who was exposed and unexposed and their case and control status perfectly. When we're dealing with this type of misclassification example that I mentioned, it means that some of our true cases are actually being put into our control group. because they're not being identified by that screening tool. So in that particular example with the PROTECT study, they asked, given our observed data, what would we expect the true data to look like, assuming that we had 60% sensitivity for our PSA test and 100% specificity. And if you're not familiar with those, I will get into what those specifically mean. But here, sensitivity and specificity, these are our bias parameters. So I mentioned, with these types of analyses, you'll use bias parameters to do these corrections in your data. And so sensitivity and specificity would be a key form for dealing with misclassified data. So we can even think about just what we would kind of expect the movement to look like, right? I showed that kind of 2 by 2 before with all the colors. And so we can think about, if on the left side, if this is the observed data that we saw, we would think that if there's less than 100% sensitivity and 100% specificity, that movement, like I mentioned, right, is that in the misclassified data, some people who are truly cases are being put in our control group. So we would expect that in truth, we should have more cases. And since it's here non-differential, we're not distinguishing between those with or without family history. So we would expect that that would be true for both of our exposed and unexposed groups. And so we'd be pulling from the control group and putting some people actually into the case group. And so that's kind of the expected movement of the data when we have this type of misclassification. So in order to do these types of corrections, it's important to think about a confusion matrix, which I love, but I know it's a lot to look at. So I wanted to walk through this with you to make sure everyone's following. So here the columns represent the true classification status for the individuals in our data set. So condition positive would mean that, they do have that particular condition, whether it's an outcome or our exposure of interest, whatever variable we're concerned might be misclassified. So the columns represent their true status, like if we knew for sure exactly what their true status was. And then the rows represent how we have them classified in our observed data. So the intersection here of condition positive for both the truth and the observed, then those would be true positives. So in green indicating, yay, they were classified correctly, right? And also for our condition negative, if they're both in truth and classified as condition negative, then they're true negatives, again, classified correctly. Folks that are classified as being condition positive, but are actually condition negative, those would be considered our false positives, or these would be type 1 errors, and they're incorrectly classified, hence being in more of a reddish color. And then those that are classified as condition negative, but are truly condition positive, those would be our false negatives, also known as type 2 error, and again, incorrectly classified. And with that prior example that I mentioned, that's what we would have going on, right? There would be some people who were not captured by the PSA test, and so they were classified as condition negative, but we know, in fact, some of them are actually condition positive. So they would be false negatives. So in case you're not familiar with the term sensitivity, would be the probability of being correctly classified as condition positive among everyone who is truly condition positive. So it's kind of like taking that like stack of people that are all truly condition positive, taking your true positives and dividing it by everybody that's condition positive. So that proportion would be your sensitivity. And then your false negative rate would just be 1 minus your sensitivity. And this is the probability of being incorrectly classified or misclassified as condition negative, those false negatives, given that you're truly condition positive. Now, your specificity is focusing in on individuals who are condition negative. So it's the probability of being correctly classified as condition negative given or among everyone who is truly condition negative. So that proportion of the sample that are being properly classified as condition negative among everyone who's condition negative, that's our specificity. And our false positive rate is just 1 minus our specificity. So it's taking those false positives and dividing them by everyone who's truly condition negative. We'll also talk a little bit today about positive and negative predictive values. And this is where you're taking it from the point of view of how people were classified in your data. So if you look at the probability of being correctly classified as condition positive, given everyone who was classified as condition positive, so these are our true positives divided by everyone who is classified as condition positive in our data set, that's our positive predictive value. And then negative predictive value would be those who are being correctly classified as condition negative among everyone who was classified as condition negative. Yeah. Okay, so you might be asking, well, where do I obtain this information? Like, how do I actually do these types of kind of corrections and look at these kind of confusion matrix? Well, the kind of gold standard best way to do it would be to use internal validation data, right? So basically taking like a nested subsample of your overall sample and then having some information on more of a gold standard measurement and then comparing their classification based on that gold standard to how you have them classified in your data. So this could be like if you have self-reported information on outcome, maybe in a subsample, you're able to obtain their medical records and look specifically within there how they are classified for that particular diagnosis. So here's an example using asthma diagnoses that were originally ascertained from the Danish National Registry, but they were concerned there was some misclassification in those data. And so they compared that classified data from the registry to among a subset that also had information in a military registry database. And they use this information to calculate sensitivity and specificity of asthma diagnosis. So here's just an example of, an internal validation study because they're using a separate set of records within a subsample to look at kind of how things are being classified under the assumption that that second registry was actually going to be more accurate than what they had in the overall sample. But internal data are not always available. So you can also look to the literature for external validation studies. And you may hear the term external adjustment, and that's what this is referring to. So kind of looking through and seeing, well, we can't do a validation study, but what other validation studies have been done? And can we identify one that we think could probably have similar degrees of misclassification as our data and then apply those parameters to our analysis. So I really love this table. This is a kind of summary of different validation studies that have been done looking at self-reported first degree relative breast cancer history. And what's really nice here is that they had this information broken out if it was done separately among individuals who had breast cancer and those that did not have breast cancer. So you could start to look at, if you had a question about differential misclassification, that might be really handy. It also gives information about which population was being studied for each one of these studies and where they got their gold standard measurement. So I am not an expert in breast cancer research, but I'm guessing for someone that is, they would probably have a pretty good understanding of, the quality of the information that's captured in these different databases. And then you could think about your particular set of subjects and how similar or dissimilar they might be to these specific source populations. And then sometimes we don't have that information either. And so you can go off of expert opinion and educated guesses and kind of look at a range of different scenarios for misclassification. You might also be constrained by how much people could even move in your 2 by 2 table, right? Because when you're dealing with misclassification, that's really what is happening, right? People are being moved from one group to another group when you're doing these corrections. And so there may be only so much movement that could happen or before you encounter like zero or negative cells. And so sometimes that can also restrict down the range of different scenarios that you could look at. So there are some misconceptions or things that people often don't really consider when they're doing a validation study, and I thought it would be kind of neat to talk through some of these. So please don't hesitate to be brave because this paper that was done, they did a big survey of a lot of EPIs, including people who are, instructors, PhDs, and a lot of them were not getting these answers correct. So this is a safe space. Um, but one of the questions that they asked on their survey and published the results of is, so they asked this question, true or false? It's usually valid to apply estimates of positive and negative predictive value from external sources, so taking these from the literature, and then applying them to another study population when conducting a bias analysis that will adjust that study's estimates for misclassification. So what do you all think? Do you think this is true, that we can take those external positive and negative predictive values, or do you think we shouldn't do that? Anyone brave? You could put it in the chat.
Jordan says false question mark. Cassie, a lot of falses coming in.
Okay, awesome. Yes. Well, good job. I don't know if that was a guess or you knew for certain why, but that is the case. This is false. You would not want to necessarily be pulling positive and negative predictive values from other studies. And the reason for this is that positive and negative predictive values are going to be sensitive to the true prevalence of whatever you're trying to correct the misclassification of. So if you had a factor that you thought was misclassified, but it was more or less common in that external data set, then those positive and negative predictive values would really not be appropriate to apply in your data because again, they're going to be impacted. They're going to be kind of dependent on whatever the prevalence is of that condition in the population. And another thing to note about positive and negative predictive values is if you're looking at an association between a particular factor and an outcome, and you have, um, let's say, non-differential misclassification, still you're going to have different positive and negative predictive values for like that other axis. So if you were considering, let's say, exposure misclassification, um, and you had a non-null, so there was some association between that exposure and outcome in reality, then your positive and negative predictive values for that exposure will be different for individuals with and without the outcome, even if the misclassification is non-differential, because of the fact that positive and negative predictive values are directly tied to how common or like how often that thing happens in your data, right? So if there's an association, then it means your exposure is going to be happening more or less depending on whether or not someone has the outcome or not. Um, and so because of this, when you're doing a validation study yourself, it's really important to stratify or kind of like pull out individuals that you're going to include in your validation study based on other key variables, like in the instance of exposure misclassification, to make sure you're getting those with and without the outcome in your sample. And if you're dealing with outcome misclassification, to make sure you're getting exposed and unexposed individuals because their positive and negative predictive values could be different from one another. if there's an actual association, even if that misclassification is non-differential. So this is a nuance that, not everyone would necessarily consider, but important to consider if you're doing a validation study yourself. Another question. So let's say we are doing an internal validation study and we sample from respondents in our study based on their imperfectly classified measurement. So let's say here it's vaccination status. So we're going to sample 100 people who self-reported as being vaccinated and 100 people who self-reported as being not vaccinated. So what parameters can we calculate in this internal validation study? So one is sensitivity of vaccination status, another is specificity, positive predictive value of vaccination status, and negative predictive value of vaccination status. So what do folks think? We do all of these, some of these?
The first two was added to the chat. Any others?
Okay, so the answer for this one is positive and negative predictive value. And recall back to that confusion matrix, we were looking at where these values are coming from. They're based on how people are classified, right? So like the denominator in both of these are among people who are classified as condition positive, this is the proportion that are truly positive. And among those that are classified as negative, this is the proportion that are truly negative. So with this design, because we're sampling based on their classified status, like their self-reported status, and we're thinking maybe that's not always correct, because it's their classified status, we can only look at positive and negative predictive value because we don't have those like denominators of like the true conditions. So if you did want to calculate sensitivity and specificity, you'd either want to take just a truly random sample of your overall group, or if there was a way for you to kind of look into whatever is your gold standard records and specifically pull out people that are, vaccinated and non-vaccinated based on that gold standard data, then you could then compare that information to how they were classified in your data set. And that would allow you to calculate sensitivity and specificity because you're specifically pulling your sample based on their true classification status. Um, but if you're sampling based on how they're classified, you're going to be stuck with positive negative predictive value, which is not a problem. If it's an internal study, then that's totally fine, right? The issue comes up if you're trying to take that from an external study and apply it to your data. That can be more problematic because of if it does vary in terms of how common it is in your data versus that external data. But thank you. Thank you to everyone who's being brave. Like, I love when people actually interact during these things. So thank you. Um, So one thing I wanted to mention, I'm not going to get into it because it gets really complicated, but there are also things called dependent errors or dependent misclassification. And this is when people are not just moving like kind of across or up and down in that 2 by 2 table, but they're actually moving across the diagonals. So this can happen if your data are coming from like the same source and the same time point. So like maybe a cross-sectional database, especially like if you're thinking about maybe like self-reported data where maybe due to kind of social stigmas, people might be reporting information a certain way. Um, then it will lead to this kind of potential that people are actually moving across the diagonals. So someone who, let's say we were doing a study of, let's see, alcohol use, postpartum, and postpartum depression. Um, you could see how maybe there are certain individuals that might fall into that group, but are reluctant to report both their alcohol use and their depression status. And so maybe in truth, they would be exposed individuals with that outcome. But because of that social stigma, they're moving from that A cell down to the D cell, where we would classify them as, being non-drinkers and not having depression. Any other like situations you could think of, either data sets or types of like association questions where you could see maybe someone moving in the diagonals? I mean, really anywhere where you're dealing with like a social stigma kind of question, it could certainly come up. Um, Sometimes we're dealing with like information that's assayed from biospecimens at a lab, and like something is happening with the way the samples are being assayed. And so if we're getting like, two variables from that same analysis that have like the same kind of like measurement error issues going on, you might also have these kind of correlated errors. Um, or like in the medical record too. Sometimes, like there might be subgroups of your population that are not coming in. And so they actually have like that condition, and they are, more likely to have a certain exposure or characteristic, but you're just not capturing it in your data set. And so that's like moving them into this like group where they would be exposed and have the outcome, but because you don't have that information, they end up being classified as unexposed and without the outcome. So the tough thing about these types of dependent errors is that the bias is really pretty unpredictable. So if you do think this was happening in your data set, it would be really great if you could do a validation study and try to understand the degree to which people are moving across diagonals, because it could have, in theory, pretty big impacts on your findings, as you can probably imagine, because of the fact that people are going from being like both like doubly exposed and with the outcome to not being exposed and not having the outcome, or vice versa.
Julie, there is a question before we get too far away.
Yeah,
If the results are self-reported, how can you determine whether they're true positives or false positives?
great question. So really, when you're doing these types of like validation analyses, you'd need to identify some kind of gold standard measurement that you could have available to you in a subset of, of the participants you have in your study. So if your main study was based on self-reported information, but let's say you were doing a study of medication use, but in a subset you could get actual like pharmacy dispensing records, then you could compare whether or not, the medications that they said they were taking to control their diabetes aligned with what they had in that other database. It still may not be like completely perfect, but if you considered it better than the self-report, um, more objective, then that could be a source you could do for that comparison. So I hope that helps. But if someone still has questions, please don't hesitate to chime in or put more in the chat. Um, okay. So some resources for doing these types of analyses. There's a great textbook. This is the second edition of it now. It's like maybe 3 or 4 times longer than the first edition was. So I think a lot's been added to it. So it's applying quantitative bias analysis to epidemiologic data. This won't focus only on misclassification and measurement errors. It also gets into how you could simulate an unmeasured confounder in your data, or handle situations where you have selection bias. So it's a really great tool. And they also have a Google site where they have a number of resources that are tied to the textbook that you can just access without even buying the textbook yourself. So that's really nice too. I'll mention some of them towards the end, but this includes things like different types of like code and macros, including SAS, but I believe they also have other coding languages, like probably R is in there as well. And something that I like a lot, just if you want to like play around with your data and try to understand like how people might move under different scenarios, they have these Excel sheets which are really great. So this is taking one of their Excel sheets they have for misclassified data, and it's using that outcome misclassification example that we had towards the beginning of the talk, looking at the relationship between family history and prostate cancer. And so this is, me putting in these cells here, the blue cells, the sensitivity of 60% and the specificity of 100%, which was non-differential. So we're assuming it didn't differ based on family history. You can specify, just so it's really clear in like the appearance of the table, what your outcome and your exposure variables are. And then you can enter in those blue cells in that 2 by 2, what your observed data distribution look like. And so we'll calculate then the crude odds ratio, which was 1.64 in the observed data. And then based on these bias parameters, what that corrected data would look like down here with a updated odds ratio of 1.75. So a slightly stronger association that was observed when considering that type of misclassification scenario. So I'll walk through one other example using that spreadsheet. So let's say we were doing a retrospective cohort study. And at the time that we were collecting our data, we knew there was some evidence out there to suggest that vitamin D may be protective against preeclampsia, and those are our main exposure and our outcome that we're looking at in our analysis. And we're worried that some of our participants who were diagnosed with preeclampsia may have then somehow differently reported their vitamin D supplementation information that we obtained because it was obtained after diagnosis. And so we decided we want to look at some different scenarios for misclassification based on external data that we have, and then calculate, our expected true association. So down here at the bottom, we have what our bias parameters were from that external study. So we had a sensitivity of vitamin D reporting among those with the outcome of 0.95, a sensitivity among those without the outcome of 0.9 or 90%, and then specificity among those with the outcome of 90%, and specificity among those without the outcome of 80%. And so if we use that spreadsheet again, this time going to the exposure misclassification tab, we can enter in those bias parameters and enter in our observed 2 by 2 data. We see that there we would get an observed risk ratio of 1.3, but after applying those particular bias parameters and people moving in the 2 by 2 table, it would get updated to be a risk ratio of 2. So a stronger association based on this particular scenario of differential exposure misclassification. So I think that's a really nice tool because, like, again, I'm kind of a visual person and it allows you to actually see the expected movement of people under different scenarios. And you could, you can actually use these arrows to bump up or down your sensitivity and specificity parameters and see, again, how things would change. So all the analyses I've shown so far have just been these kind of simple bias analyses, but you can also do a multidimensional analysis. So this would be where you actually look at kind of a range of different scenarios. Here's data again from that PROTECT data set, this time looking at the association between diabetes and development of prostate cancer. And then for this analysis, they didn't actually restrict down to just kind of one set of bias parameters for the corrections. They were curious about a range of different scenarios of outcome misclassification based on diabetes status. So down in the bottom part of the table here, you can see kind of all of these different like settings that they put their sensitivity to, always keeping their specificity at 100%, thinking there aren't any people that are going to, through that PSA test, actually be bumped into being classified as a case, even though they weren't a case. So if you're not having any movement of not truly non-cases to like misclassified cases, then that would mean you have 100% specificity. So you're not worried about that happening. Um, but here they did were concerned about imperfect sensitivity. And so they looked at this different range of scenarios depending on your diabetes status. And then what's cool is they plotted this out. So they had like all of those findings that I showed there, and then they plot them out here where you can kind of see how the odds ratio would be expected to change based on what they originally observed if they did these types of corrections under these different assumptions, with the x-axis here representing the range of sensitivity in the individuals with diabetes, and then the colors, different colors representing the sensitivity among individuals who don't have diabetes. So it's like there's a lot of information shown here, but I wanted to show this as a way of like you can actually deliver a lot of information, and these analyses can be quite powerful, using like a visual like this and a figure and showing all of these scenarios, which I think looks a lot nicer than just looking at this table down here, even though they're showing the same pieces of information. Then I briefly just mentioned there is also probabilistic analysis, which is really more of a kind of simulation sort of analysis. And here we're actually able to incorporate both kind of the influence of random errors from our data through like sampling and sample size, in addition to these more systematic errors to understand total study error, which would be indicated by the width of our confidence interval. Um, sometimes we refer to the simple and multidimensional analyses that I mentioned before as deterministic methods because they're not incorporating this degree of uncertainty or like random error that a probabilistic analysis can. But probabilistic is definitely more analytically intensive. And so I recommend always starting with the simpler model first, just to understand like what happens as you adjust the parameters and how people would move, and make sure that whatever you're modeling makes sense first, and then you can move to something that's more complicated, like a probabilistic analysis. And so briefly here, when you're dealing with a probabilistic analysis, you're actually going to specify an complete distribution for those bias parameters. So it wouldn't just be like, oh, we think sensitivity ranges from 20% to 100%, but we also think that most likely it's probably somewhere between um, 60 and 80%. So if you actually look kind of the distribution of these different scenarios we're going to test out, it would be like this kind of figure down here on the left side where you'd actually see for a range of sensitivity scenarios, the majority that we're going to simulate are going to fall in a certain area. But we will also look at kind of these tails, these more extreme scenarios to see what their impact is as well. And here, not to make things complicated, the sensitivity is broken out and there are two plots, two different distributions, because one is representing like one site and the other one's representing a different site in these particular data. But you wouldn't necessarily have to do it that way. That's just how it was done for this particular analysis that I'm showing here. Um, and then here you can see on the right side, this is the specificity that was defined in this probabilistic analysis. So you can see they really didn't vary specificity that much. It looks like it goes from 0.98 to 100%. So pretty high either way. Um, but the vast majority of scenarios that they simulated drew from scenarios where there was basically 100% specificity, very high specificity. So basically what you're doing is you are coming up with these distributions, and then you're going to run like many different iterations of adjustments in simulated data sets to look at all of these different combinations of scenarios based on these distributions. And then you'll summarize across them, usually with like a median and then maybe like the 2.5th and the 97.5th percentile among all of the results that you got back to be like a simulation interval. And I think, yeah, I have one example here from the literature. So this group of researchers was interested in evaluating the impact of ICD coding errors based on how preeclampsia is classified. And they performed a probabilistic analysis using a SAS macro, which I believe is available on that Google site that I mentioned. And they based their results they based their bias parameters using validation study data. And they did assume that preeclampsia misclassification would be differential based on a woman's BMI. And so they used BMI specific sensitivities and specificities based on their validation data, simulated a bunch of different scenarios in 10,000 data sets. They looked at 10,000 different combinations of sensitivity and specificity based on BMI. And then they summarized using the median and then 2.5th and 97.5th percentile to kind of get at that like central corrected estimate and then like a simulation interval around them. And in the end, they found that the bias analysis results were less precise, which makes sense, right? Like, because we're dealing now with like incorporating both like random errors and these systematic errors that might be happening in the data. So this would reflect, a greater degree of uncertainty that they weren't detecting in their original analysis. But overall, they found that like central point of tendency with those corrected estimates did suggest that in the observed data, there was a bias towards the null. So the results got stronger after they did the bias correction. But ultimately, they felt like it didn't really alter their overall conclusions about the association that they were looking at. So you can probably imagine that this does get kind of complicated and is can be more computationally intensive. So I'm not going to go through it in detail really today, but I wanted to mention it to you that it is available as an option if you did want to kind of go to this length. And there are, again, that textbook and the things that are on that Google website have resources to be able to run these types of more like simulation-based analyses. And was there maybe a comment that came up in the chat? Thought maybe something popped up, but maybe not.
Nothing new.
Okay. All right. So it is getting pretty close to the end of what I had prepared for today. So here are some coding resources. So this is that SenseMac SAS macro that was mentioned in the paper I just mentioned. It is on the Google site for that textbook. There also are a number of papers, and again, I can send out a full list of what these resources look like, many of which have coding resources attached to them, like through a link or in their appendix. There are also some pretty cool R Shiny apps where it's doing similar types of stuff as those Excel spreadsheets, but they have some other visuals that they make. So those are kind of nice to look at as well. So I'll make sure this all gets distributed after our call today. And then I'll just wrap up with going through some, best practices when you actually are kind of presenting and interpreting these types of findings. So really this is considered kind of like, even though it is a sensitivity analysis, there's this whole set of assumptions, right, behind the bias analysis itself. That's right, with like getting all of your bias parameters and then, where those came from. And depending on the type and complexity of your analysis, you're going to have these kind of range of different scenarios that you're looking at. So you want to be really clear about, what is the objective of your bias analysis? What are the assumptions that you're making? You want to be very clear about, the bias parameters that you used and where they came from, the basis of utilizing those bias parameters. Nowadays, if you are publishing this or if you're putting it in a report, most things are online. And so usually you're not stuck to using a certain word count, and you can put this information in an appendix for your report or your paper as needed. Um, and tables and figures are really helpful for presenting your results. I think especially figures, and sometimes they can help you, identify patterns that you don't see necessarily up front when you're just looking at the results in a more tabular format. And then it's always good to talk about, a description of how you would maybe change your original interpretation in light of these findings, right? Are you less confident? Are they affirmatory? Do you not really change your conclusions based on the results of your bias analysis? And then when would you actually go about doing a bias analysis? So if you're doing a project and you're getting something that is very much in line with what you would expect, you've seen that same type of prevalence and associations between that exposure and outcome and other studies as well, then maybe not necessary, right? Because you really are seeing something that's consistent with what you would have expected to see. If you are finding something that, you know, is a pretty weak association and you think there's potentially possible alternative explanations for the results that you're getting, it might be a good idea then to look at this, even if it has been seen in other studies, because maybe they didn't consider the type of bias that you are considering here. If you are trying to draw inferences about causality or about, decisions that would be made in terms of like an intervention based on the findings of the project you're working on, again, probably a good idea to look into this before resources are poured into that. And certainly if you're going to make some kind of like policy recommendation, this would be a really good idea to look into these types of things, because often we are, in observational settings, like our data are not perfect and often are misclassified. Or like I said, you can also do these types of analyses for unmeasured confounders or a selection bias issue. Um, and, these types of analyses are good, I think, in these times when we are dealing with limited resources, because, we wouldn't want to pour in funding to something that in the end really wouldn't be very effective in trying to do what we were originally hoping to do. So this is pretty minimal effort in order to better understand and quantify the potential influences of these types of errors. And so that wraps up what I was planning on going through today. So if folks, have questions and want to stick around or talk through anything that they've encountered or dealt with in their own work, would love to hear about it. But thank you all for listening to me for roughly the past hour.
Thank you, Julie. Any questions?
And like I said, I know I went there a lot today, so I'll make sure, all of these papers that I mentioned, especially ones that are more like tutorial kinds of papers, and then the links to these different coding resources and spreadsheets and our Shiny app stuff is available to you. So you don't have to remember everything from today.
Mhm. Wonderful. Okay. Yes, we'll make sure we will get those resources to you, the slide deck, the webinar as well, and an evaluation.